Hi, and welcome to Java Programming 3, Session 3. We're going to be talking about software testing and the importance of software testing when we are writing software. Our agenda for today is what is software testing. We're going to discuss the terminology, what is the TDD development cycle, the do's and don'ts of TDD, how we're going to do some test development, or at least the tools that we're going to use for doing some test-driven development, what is JUnit, what are mocks, and we're going to then do some exercises. What is testing? What are software tests? Well, software test is just essentially using software to test other software. The idea of this is to automate these things as much as possible so that we don't have to be repeating steps over and over and over again. The idea is that you can make things a lot faster, more predictable, and it allows a developer to just make sure that everything is running smoothly. And why via software? Why not? I mean, it's fast. You can set up things so that it's repeated and it's not boring. It's a lot faster. It's automation. Automation is going to run the world. Okay, so then let's just make sure that we are on the same page about every term. What is the code or application under test? Well, it's essentially the thing that you're going to be testing. It's what you're going to be just using software to verify that things are actually looking okay and working correctly. What is a test fixture? What is a test fixture? A test fixture is a precondition or is a piece of information that has been defined before. So, for example, a database. In Django, in Python, for example, there are mechanisms of reloading the entire database into a system before it is tested. So that way you can have a series of preconditions just inserted into the software and making sure that they're consistent. A unit test. A unit test is probably the smallest unit of testing. So for example, if you're going to add two numbers and say you're going to test that you can do 3 and 5, and that's going to yield 8, and then you can just test different numbers and making sure that that at the smallest function possible that the software is doing what it's supposed to. So it's essentially breaking it down by units to the smallest thing. Integration tests. Well, if you have a bunch of unit tests, and in reality your software is not going to be like this tiny thing, and your software is going to be all these things that are in the system that are going to be interacting with each other. So an integration test is just a way of improving or testing. It's just a way of testing everything from A to Z of what the software is. And that means how components interact with each other. That also means how something is being clicked. For example, if you have an application, it tests how system A works with system B and system C, or all the dependencies of the system are working together. Performance tests. Performance test is just, you can brute force something to work, but that doesn't mean that it's going to be effective. That doesn't mean that it's going to be fast. So a performance test, what it allows you to do is that it allows you to make sure that you measure that the system is working and doing what it's supposed to do in an accurate way, or in an ideal way. Performance test just helps us benchmark, so that way, say that you have a web browser that is not consuming your entire computer. I don't know if a lot of you probably already have noticed that having a few tabs open on your Chrome browser is gonna bring down even the best machines in around. So a good practice for good user experience is to also run performance tests. And there are two other concepts that are behavior and state testing. Behavior is essentially testing the interactions of an application. So for example, if you have an app, a mobile app, and you're going to be clicking on the button you are just going to be making sure that the interactions of your application are going to be correct. In a state thing, it's essentially just the same thing, but it's just slightly different. A state is if I press A, will it change the entire state of the result of the application into another screen. The other one is just making sure that the things respond correctly. One is about the interactions, the other one is about the change. So for example, to put it in the simplest terms possible, let's say that you are going to test the behavior of walking. It's not the same as if you have something running in a treadmill because you're not advancing. But if you're actually putting the same person, the same movement in a street, you're going to see how that person is going to move. That is the state. The state is actually changing position. If you're just testing that the behavior of walking works, then doesn't matter if you put that person on the street or on a treadmill, you are going to be testing the behavior of walking. Okay, so what is TDD? TDD stands for Test-Driven Development. TDD is a philosophy about testing your software before you write it. Testing a software before you write it? How is that possible? So in the TDD lifecycle, you have 3 stages. The red stage, which means that you got to think about what you want to develop, meaning the test. You are going to write the initial simple test. Then on the green stage, you're going to think about how you're going to solve the problem. That means writing just enough code to make the previous test pass. And then you have the refactor cycle, which gives you the where you go in and improve so that you can write another test, and so on until you have much better code than actually had you just written it. Let's assume that we're going to create a Fibonacci test where we are going to determine how many Fibonacci numbers that we need and an output of that number. So say that we're going to do the 5th Fibonacci number. That means 0, 1, 1, 2, 2, 3, 3, 5. If you remember the Fibonacci sequence, that means that it's 0 plus 1 equals 1, 1 plus 2 equals 3, 3 plus 2 equals 5, and so on. You're always adding the last 2 digits and the last to generate the next one. So let's assume that we're going to be saying that our 5th number is going to be 5. So we're going to provide 5 and 5, and then we're going to write enough code on our Fibonacci sequence to try to get to the 5th number and then make sure that it's returning a 5. So then once we go and then do another, when we refactor, just to make sure that we're covering enough for longer sequences, so that say that we want to test for the 150th number, then we can go and then verify that via TDD. The nice thing about this is that it makes refactoring really easy. Refactoring, it comes out of the straight out of the box because you have enough unit tests to make sure that you are not breaking something, especially really useful when you are dealing with super long code bases. Okay, so what are the laws of TDD? You never write any production code until you write one failing unit test. So you never go into code writing until you have a piece of test that is actually failing. Why is that? Well, because you just want to make sure that you are solving tiny little pieces at each time. And how can you write something that is not failing or that doesn't need to be fixed? You need to have something that needs to be fixed in order to continue. The second law is that you cannot write more than what is needed for that little test to fail. So in the case of the Fibonacci thing that we were talking about, we are not going to move into the next iteration or into something bigger until it's not needed. So we only solve that smaller problem first, and then once we go into the next iteration, then we'll create a bigger problem, slightly bigger problem, then we'll solve for that problem, then we'll create a slightly bigger problem, and then we'll solve that problem. Essentially making sure that as we're going through that red-green refactor cycle, that we are writing the right code. The third law is that you can write slightly more code in order to make the test above fail. So essentially, it's a cycle that until you have no more failures, then you probably can be happy with it. If happiness can never be achieved with software development, because sometimes you deal with inefficiencies. And even though that your code might be correct, it might be inefficient. And that is where algorithms is an important topic. Okay, the next thing is that we're gonna deal with TDD Anti Patterns. What not to do with TDD practices. So what not to do with TDD practices? We should not have a test case that depends on the system state manipulated from previously executed cases. So what does that mean? If you don't have a way to reproduce the current state, don't do that. Just don't try to overcompensate or that one test. What does that mean? That means that the previous test should not be modifying the data that then another test is going to grab. Seems counterintuitive and seems not very efficient because you're constantly resetting and going back to the beginning, but software is so fast that it doesn't really matter as far as that goes. But what it does matter is that you can guarantee that your state will pick up that little unit test, will work with that data regardless of something that could have broken the test in the background. Then what's another anti-pattern? Having dependencies between tests. That means that if you have a complex system, don't really go and grab another object from another thing that might change on the underground, or at least try to minimize it. You know, software with open source and all these things that you can use certain libraries, you probably need to rely on some of those dependencies. But if you minimize it, you will guarantee that your algorithms will be a lot better. Execution order should not be relied upon. That means that if you run test A and then test B, and both succeed in that order, if then you flip it and test B runs first and then test A, and then all of a sudden things fail, it's breaking, first of all, the previous anti-pattern about the state being changed by a test, and also the execution order should not be needed. And that also leads to our next anti-pattern. That means that that interdependent tests can also cause cascading false negatives. That means that you could get a false negative by one of those just changing the status in this of the current system. Another thing would be like just making sure that some performance is guaranteed via TDD. I mean, in some cases you just have to like allow certain timeouts and things like that, and if something doesn't happen within a reasonable amount of time, well, you know, it should be flagged. But also you shouldn't be expecting something to happen at a certain speed, especially in the microseconds thing, because sometimes you might be running your test in machine A and then sometimes in machine B, and machine B might be a lot smaller or slower than machine A, and then you're just shooting yourself in the foot by assuming that everything is going to run in the same way or in the same performance as it did on machine A. The other anti-pattern is building objects that know everything. And by that, it's just that you're putting too much information and you're putting all your cooks in the kitchen. And with that, it's not really recommendable. In the same situation of slow or performance, slow running tests, I mean, you might have something that it's actually timing out, and that is something that should be flagged. And that's why running a slow running test is also considered an anti-pattern. Okay, so this is where we go into the meat and potatoes about how to test using Java. So Java is utilizing, we're going to be using for unit tests, software called JUnit. JUnit allows us, it's really simple because all you have to do is use Java annotations to define how the thing will be executed and what are the things needed for the execution. So for example, if you want to do an annotation via your, for example, if you want to specify that a function is a test, then you can use the test annotation so that it can actually run as a unit test. It also provides a bunch of assert functions that are convenient enough so that way the program will crash. This is where you want things to crash if it fails. And that's where unit testing is ideal for that. You want to make sure that the behavior is expected, and if it fails, then it should stop any extra execution until that thing is fixed, until that problem is actually solved. So the assert methods essentially allow us to execute or break if a condition is met. So for example, if you have a piece of software that it's adding two numbers, and then you provide the parameter 2 and 2, and then a 4 as in 2 plus 2 equals 4, and then you're going to assert that the return of that function with such parameters should return a 4, but it returned a 5, and your operation is an assert equals, that thing is it should crash because certainly 5 is not equal to 4. This will make a lot more sense once we are writing the test, trust me. Also, JUnit provides runners to help determine how things are going to be running. Okay, so how do we create a test? And in our example for our class, I'm going to just do a Fibonacci generator. And this class, the best way to, let's assume that we are going to public int, let's do a long Fibonacci or get fib. We're gonna call that function get fib because it sounds hip. And we're gonna right now just return 0 so that it compiles. How do we create a JUnit test? The easiest way is by using the Alt key and then hitting enter. Here you're gonna get your create test menu, so you can use that, and you're gonna get this handy thing. Make sure that you have JUnit on. That if it says JUnit for library not found in the module, then you just click fix and it's going to add it real quick. You can then select if you want a setup or teardown. We're gonna go into that in a few minutes. And then also we are going to select which functions to create a test for. Don't worry if you don't have the functions defined yet. You can always define them manually. So we have our JUnit test here. So right now we're getting a problem here. As you can see, it's red and it's also running this in red. So if we go into Alt Enter, IntelliJ pops this handy menu where you can select add library JUnit 4 to class path, and that's going to solve the problem. Essentially then we get our super cool function where we are going just to test our Fibonacci structure. So going by the TDD parameters, we gotta first write a test that it's going to fail. So in this case, we're going to do a Fibonacci. We're gonna use a Fibonacci generator, fg equals new Fibonacci generator. if we right click on this thing, we can go into the Fibonacci generator test and run it. This guy here, run Fibonacci generator test. And we can see that it finished running the code quickly. So then we have run a test, it ran successfully. So then we cannot really move on because the first law of TDD is to write a test that should be broken. So we need to make sure that we're breaking the test. So if we do G for our Fibonacci generator and we say get fib, and we are going to say that we're going to pass the fifth number, and then we're going to get a number 5. Okay, so now we have a syntax problem, because this function is supposed to be getting int a, or position int okay, so using this structure, if we do assert equals, we're gonna say the result, and we're gonna expect a number 5. Okay, so now let's execute our code. Everything compiles, everything is green. We're gonna run our code as Fibonacci generator test, and guess what? We are getting a first problem saying that fails not equals the result of what we got. It is not that. So expected was 0. Oh, and actual is 5. So actually what we should do, yeah, so we were expecting a 5 to equals 5, and actually it should have been 5 to result, just to keep, you know, we're expecting a 5 and we got this. So if we run the test again, we are going to get we were expecting 5 and we got 0. Okay, so now let's go into the green phase of TDD. So let's start with int first, int second, and then for, so let's do that 0 is the first, the second is 1, and then int counter equals 0. For, actually, let's go into, for int counter equals 0 until counter less than position counter plus plus. So we are going to do first, oh, and then let's do long result equals first plus, well, let's just do 0 at this point. And then we're going to do result equals first plus second, and then we gotta advance. So we have first for second equals this. So then now first equals second, second equals result. So we're moving the pointer from oh, we gotta cast it into a, let's just change this to all of them to longs, so that way we're dealing with big numbers. Okay, long, yes, long. Okay, so we're essentially grabbing 0 plus 1 equals 3, and then essentially we're grabbing the next one and then continuing that way. So what happens if our Fibonacci generator test, if we run it now, ooh, we're getting 0. That is because we never really returned the result. So now let's go and run it. So we got 8. Okay, this is where we use the debugger. So let's debug Fibonacci generator test. So then first and second, 2 is 0 and 1 equals 1. So this one is 1. 1 and 1 equals 2. That's our second jump. It was from here to here. then our third jump is to 5. You're gonna see how on our third count here, it goes into the result, which is 3 and 2, 5. So I was in my algorithm, I am doing not the positioning of this guy, but the amount of jumps. That means that my jumps are always going to be 2 spaces behind. So my position should always be is 1, because we're going 0 and 1. Those are the 2 first steps. 0, 1, that's the second position. First and second, that's the second position in that case. It's confusing just the way that arrays are counted, but in this case, it's actually doing it correctly. So then what happens if in our test, we want to test something like the position 10, and then we're going to compare what 10 is supposed to be. So 5 plus 3, that's 8. That's the 6th position. 6 plus 5 is 11. Let's write it down. 6 plus 5 is 11. Let's write down in a note thing. So we have in our Fibonacci, we have 0, 1. We have 2, 3, 5, and then 5 and 3 is 8. 8 and 5 equals 13. Equals 13. Then 13 plus 8 equals 21. And this is an actual good way of seeing it as lines of code in another text editor. Then 13 plus 21. 13 plus 21 equals 34. And then this is going to be 55, the next one. So if we put 55 and run the test again, the process finishes correctly. So our code allowed us to work correctly and make sure that actually if we go and refactor this thing, we're gonna get the right number. So there's another interesting thing to in JUnit that it's called the coverage. That means you are going to test how much of your code you have been testing and how much your execution actually worked on. So if we want to test that, it's really interesting because you can just go and run Fibonacci test generator with coverage, and you're going to get this handy dandy table, which in this case for our here, it's going to say that we covered 100%. If we see this, we get green lines when that means that 100% of the classes here that test used were covered, 100% of the methods, because we're testing the single method, and 100% of the lines. You can see all the lines that are in green when something runs with coverage, and you will see in red the lines that didn't run. So you can then see what is the percentage of the code that you're actually testing. And ideally, the closer everything is to 100, the better. Okay, so we wrote a very quick test, and the idea is that with the annotations, as we saw in our JUnit code here, let's in our test here, we saw that we have the test decorator or annotation, and this essentially says that if we use the at test annotation, it's going to define our method as a test, something to execute. If you use the at before, something will be used to prepare the test, just initializing classes, or it could be loading fixtures, etc. After, things that are going to be run after the test environment, and that is before and after each test method. So for example, something that allows you to save some memory, close a database, remove a file, things like that actually are really useful to essentially return the state of the machine to 0. or set it up so that you can execute the test. We also have before class and after class, and it's essentially the same as before and after, but the thing is, like, it only runs once per each class of that you're executing as a test. So it's really useful, so that way before and after is run after each function in the unit test, and before class and after class is running on the class per se. All right, so ignore, or it's just a way of disabling the tests. It's just if something is failing and you just want to figure out and continue with your development, you can ignore that unit test. Then you can also force certain exceptions to happen, and just to make sure that, you know, whenever you are testing for a problem, and making sure that sometimes an exception is an actual good thing. So for example, if you're testing that something that should not happen happened, are you going to warn the user? So this allows you to catch that exception, and if it doesn't happen, then the test will fail. And also you can, between parentheses in the test method, you can pass how long that test should be waiting for something to happen, as far as a timeout goes. Okay, so then what are the asserts? The asserts are the functions that you're going to compare something on the execution of your code to happen. So for example, fail will force something to fail, and that's sometimes something that you want. So for example, if you have parts of the code that you didn't want to reach, but it actually reached that, failing essentially forces that to make sure that you're not doing something that you shouldn't. You know, it's just as a safeguard. Assert true just compares the condition to the result that you got, and if it's true, then it just verifies that it's actually true. Assert false is going to verify that the return of that function returned false. Assert equals is just going to compare it and make sure that they're the same. And for a certain floating point, there is also one with a tolerance. So that's also something good. As you can see in all these functions, there's a message, and sometimes the message is what you can write in case of a failure. Assert null is just making sure that something that you received was null, or assert not null is that you actually got a value. And assert same is essentially, if for those of you that have taken Java 1 and Java 2 with me, I always insist that the comparison between a dot equals method, for example in a string, versus an equals is not exactly the same. This is just assert same is just going to compare that you are mapping to the same object. And assert not same is also useful for whenever you want to just double check, for example, deep copy, and you want to make sure when you're going to compare a deep copy, and you want to make sure that you're not referencing the same object. In some cases, JUnit, you cannot just be writing like all the expected values in your test, so you need to figure out ways of passing parameters into the code. And sometimes, you know, it could be like things from a long file or things like that. And okay, for parameters, we also have this file called hello world parameters test, where I am defining a list of names that I want to use, and then I'm going to test the greeting mechanism. So I'm going to check that for each one of these guys, for each one of the Beatles, I'm going to just make sure that the hello greet, the hello method, which is this guy, will return a piece of code that contains a string. For example, if I am passing John, it's going to contain the name John. So for example, if I am going to run this parameter test, it just finishes correctly. How do we know that it's actually doing its thing? Well, let's use the debugger. So let's go into this guy and put a breakpoint in this line, so that way we can see how the parameters are being passed from this list. So let's just debug it. And the first thing is that it's getting hello John. So it got that John from the parameter test, this guy, And if we continue to the next step, then if we continue, where is this? If we continue, we're getting Paul. And if we continue, we're getting George, and then we're getting Ringo. Again, in our parameters, when we are saying parameters, add parameters, is going to start calling this constructor with each one of those items. So we are essentially, if we split it into a different line, if we also put a breakpoint and then we run that test as a debug, it's going to be going into first initializing for each one of these guys, is initializing with the parameters for each greet function. So essentially, the greet function is being called 1, 2, 3, 4 times with different objects, which is this hello world parameter test, each one receiving a new name. So it's essentially creating 4 objects. So for example, just to prove it, we are creating a hello world parameter test at 1212 with the name John. If we go into the next one, it's doing 1233 with the name, let's just continue to this, 1296 hello world parameter test with the name Paul, and then hello world parameter test at 1311, etc. So for mocks, we have a library called Moquito, and in Spanish that might be actually really funny because that means booger. But it's just the author thought that they were making something that it sounded like mojito, and even the icon is a mint leaf, kind of like in a mojito. Anyway, to install Moquito, you have to go into the project, into the file, project structure, and let's remove it so I can show you. So in the file project structure, and then in your libraries tab, you can hit plus and then select from Maven. We type Moquito, search it, and we look for the best Moquito that we can find. We're gonna go for Moquito Core. We're going to go for Moquito Core 2.234, and I wrote this Hello World DB class that it's on the repository that is posted with a class in GitHub. And this is just a function that was pretending to get a list of names. In this case, it's returning nothing, and that is on purpose. It's pretending to run that get DB names, which we're gonna, in theory, it's gonna get like a list of names from the database. And our Hello World class has all these hello and greeting mechanisms. So for example, it's going to get the names, it's going to have an access to the database, and for example, greet from DB is going to get all those names, and for each one of those names is going to essentially say hello and that name. So how are we going to test that our mock? We're going to generate a mock, and a mock is essentially a placeholder for an object that, as TDD said, you should not have dependencies. So we're gonna just pretend that we have a database access and we're getting that list of elements. Inject mocks is the object where you are going to inject the mock of the database from. So for example, in our hello world, we're going to essentially fake this object, and we're going to be able to pass and replace that object with whatever the mock is. So for example, here, we're gonna test greet from database, and we are going to just essentially create a list of names, and when we have this function when, and this is the method that it's like get database names, then return something else. So it's essentially going to pretend that hello world DB that it's mocked, when you call it, is going to return a list of names that it's called first and second. So if we run this guy, hello world test, even though that the database and I did it on purpose, the database has no names here. The test returned hello first and hello second. That is on purpose to really show that the mock is replaced by the class inside of hello world, which is this greet from DB. If we go into this, it's going to try to get it from this database. It's being replaced by our mock, which is DB. So anything inside of hello world DB, we're marking it as a mock. And inside of this hello world, that DB object, because we're injecting it, the one that has this name and this type will be replaced by the object that we're creating a mock. And then essentially we're also defining the behavior, this pretend behavior. Again, when you say when, and then the function, when you call that function, then return whatever I'm telling you to return. So it's not really doing the database access. It's just essentially pretending inside of the hello world mock hello, which is this object, and it replaced the other fake database in here. Now we can run this guy, and we get hello first and hello second, and it looks beautiful. Okay, so the Mockito basics, as we saw in the example, we have the @mock that essentially creates a pretend object. We have also the @inject mocks that whenever we want to essentially create that pretend object and inject it into another object so that we are actually removing the dependencies, we can use @inject mocks, and it's going to grab any object that we had created with the @mock and replace it inside of that @inject mocks object, essentially removing the dependencies. And then whenever we're calling the code, we're going to be using our when function and saying when we're going to call this other function, then return that other value. We're going to be pretending that we're not going to do any of the other code. We're just going to say when this happens, then just return these values. Okay, so I hope that actually gave you a good understanding of IntelliJ using JUnit and unit tests. And now let's do some exercises.